My name is Matt. As you might have guessed, being at a research software engineering conference, I am indeed a research software engineer at the University of Sheffield. So I've been in the team for 5 years or so. I've got a bit of a background with doing high performance stuff. So for my undergrad dissertation, I did work with OpenCL. I've been through some CUDA stuff, working on pulse team particularly with plain GPU. And now I had a bit of time between 2 projects to have a dabble with AMD GPUs. Without further ado, we'll get into it a bit. So throughout this talk, I would like to keep the scope quite wide, because some of you may have a lot of experience with GPUs. Perhaps some of you haven't used them before at all. So we'll run through a brief introduction on kind of how GPUs work, how they differ from CPU computing and serial computing. And then I would like to have a little look about what the AMD ecosystem is like now in terms of support, what it's like to use. Then as part of this work, just to kind of have a good comparison, I put together a little suite of GPU primitives. These are not super heavily optimized. It's kind of meant to be a resource for just kind of a direct comparison, so you can easily see what the code looks like in CUDA, how it looks in AMD equivalent. And I'm hoping that these are quite a useful community resource as well. If somebody's just getting into parallel computing, you can look at some common algorithms, see how they work in the parallel version. And we'll have a little talk about what my experience was like of doing a bit of pip and ROCm coming from a CUDA environment. So I set out a couple of kind of goals when I started this work. These were metrics I was going to review against. So I think things like the support, features, tooling, the library availability. Obviously, we're not just using like we'll write everything from scratch all the time. This is quite important, and just kind of the general experience, documentation, how to try and pick up and learn. And then there are also some kind of tools that have been designed to help you support your code automatically if you have an existing CUDA code. And looking forward, there's a couple of things that are maybe trying to sidestep ROCm altogether and let you run CUDA code directly on AMD devices. So to start off, I wanted to kind of put this in the scope of scientific computing. For the purposes of this talk, I'm really talking about simulations and models. So these might be things you might run on a consumer device in your office, through to HPC kind of scale. Might be very compute-heavy applications. Obviously, AI is a huge topic at the moment. A lot of people might be interested in that. Through to doing like parameter searches, where you're running a lot of the same kind of simulation. Interested in finding parameter spaces and searching those. So why do we use GPUs? Obviously, we've just mentioned that you might have either a performance requirement, you might have a very large problem to solve. And GPUs are good at solving large problems if we're able to break them down in such a way that we're doing lots of the same thing at once for different items of data. We can perform a lot of iterations very quickly, and yeah, we just really get this performance out. It lets us do bigger problems, lets us solve them faster, lets us run it more times. So lots of scientific computing applications are well suited to this. So we've got neural nets with AI, very famous. Agent-based models, so that's a lot of where the work that I do is with agent-based modeling. Some kind of finite element formulations and things like this can all be broken down to work well with a GPU. So when we're developing for GPUs, if you're coming from a kind of serial background, there's a couple of different things we have to think about. We have to think about how we transfer data between the kind of host machine and the device. We have to think about how our function is going to be executed. We don't really want to be doing things just like one per data item over and over. We have to think about the data dependency and try and arrange things in a way that we can do everything in lockstep and then move on to the next step. So that often involves some kind of message passing or communicating between threads, which would be a single execution thread on the device, or between iterations of an algorithm. So in terms of like what a GPU programming platform looks like. But at least for CUDA and HIP and ROCm, which is AMD equivalent, we usually use something called a kernel, and this is the actual code.
Swap to that.
Yeah, certainly, no problem.
Just
Okay. So a kernel is a function that you're going to run on your GPU, and this is kind of the code that actually gets performed on your device. And we also need some kind of API for launching these kernels and shipping our data back and forth. So we're always going to use parallel algorithms, which again is quite a different way of thinking if you used to work with serial code. So I'm hoping that this library approach put together will be helpful if you're having to crack it out for the first time. You can go into these common thoughts and searches and things that we would do, stuff like that in a parallel equivalent. So to get a little bit into HIP and ROCm, I started off, I'm quite sure what the difference between as well. So HIP is the heterogeneous computing interface for portability, and this is really what you would use to write this code if you're developing for an AMD GPU. It's kind of a default programming model. You can also use like Pickle or OpenCL, these which have ROCm backends for AMD class. But AMD kind of main intention is to use HIP. And it's very, very close mirrors to your API. If you've worked with HIP before, you'll find it very, very familiar. And AMD is like with the new version HIP coming out too, and ROCm, and we're moving even closer to your API. It's a very high error, and if you work with it, quite a reasonable time. So the API is quite wide, and part of the idea with it, what they do is that you can compile your code down to CUDA as well. So it isn't just something for AMD GPUs. You can also write the code once and then compile down to NVIDIA or AMD's portability is via an port.
Sorry, can I just take my off you?
Yeah, of course.
Just
this, yeah? Yeah, no problem. Third time round. Can you still hear me at the back okay? Yeah, perfect. All right. So yeah, we've got this kind of platform agnostic goal and we're working towards. So ROCm then is the software stack. This is originally stood for the radio Open Compute. Open Compute, I think, got trademarked or something, so now it's just ROCm. But you can see where it came from. It's open source, or I'm slightly reluctant to say this after Amanda's talk. I haven't checked whether it fits all the license requirements and things. AMD state it's open source, and you can go and look it up on GitHub. And yeah, this is kind of the execution platform for the AMD GPUs. So we've now got HIP, your host code, and that will compile down to a ROCm application. So the programming model will be very familiar. On the host side, we'll set up our program, we'll set up our data, transfer it over to the device, and we'll launch kernels in just the same way that you would with CUDA. They're very familiar. It's going to execute on the device, and we can fetch our results back again. So again, if you haven't worked with parallel computing before, we have this kind of single instruction, multiple thread or multiple data model. And the idea is that we're going to perform the same operation on multiple bits of data. So where in serial programming, you'd have a for loop and you'd step it through each item once at a time. In HIP and ROCm, we're going to launch a series of threads in parallel, and they're all going to perform that operation, each on their individual data item. So we have this hierarchical model. I've actually used the kind of CUDA terminology here because it's more familiar. AMD, I guess, to try and make it not too much of a copy of CUDA, changed a warp into a wavefront and some things like that. But you'll find the terminology very familiar, and you know, it's not a big jump. Fundamentally, the architecture is very similar. We've got this hierarchical model, and kind of a warp or a wavefront is the fundamental execution unit. So all the threads within one warp will perform the same action as this step through. So you can also have some level of interactivity via caches at each of these different levels. So in terms of OS support, this is obviously, historically, if you've got any familiarity with this, been quite a touchy area perhaps. This is kind of the list of what's supported from AMD's website, which looks quite promising. In practice, it's kind of true and kind of not. There are a lot of limitations on which versions are supported on which platforms. So it's improving, I would say, is the state of things. Ubuntu 22 and 24, generally pretty solidly supported. The other Linux variants, for some of the more recent versions of cards, you're pretty fine. Windows, the support's been picking up a lot over the last year or two. So we've brought in kind of WSL support, and either now or with version 7, we're getting access to kind of the full HIP SDK, I think. And then beyond that, there's kind of some of the AI libraries, which maybe were not still supported. So I think with version 7 of the HIP ROCm SDK, there should be full support for PyTorch native on Windows and some of the other major LLM frameworks. So I think with terms of OS, it's getting better. I think if you, we'll move on briefly. So in terms of hardware support, again, this has also been a bit questionable historically. AMD have kind of 3 classes of GPU. We've got the data center, professional and consumer classes. Support for most of these goes back 5 or 6 years on cards, but they do have very varied levels of support. And again, this has been a big concern, I think, for people considering AMD GPUs. I think in the worst case, we had a card was released, it didn't have ROCm support at release, received support for a period of 6 months and was then dropped again, which is not great if you're trying to, build a long-term thing out of this. So I think AMD is kind of verbally committed to new cards having support on release. Quite how tight a commitment that is, I'm not sure, but it's looking very good. I think for the data center cards, seem to be very well supported generally. I think they receive the strongest support. Once you get down to the kind of consumer level, it's a bit patchier. So depending on the scale of your application and what you're working with, you might have different considerations here. So I think now we're getting a bit more into the experience of things. So the documentation I found really, really good. For like an introductory level, if you're just having a go with it, or you haven't used GPU computing before, there's some really, really solid stuff, very well organized. There's nice introductory sections, installation for every single platform that they supported. And there's a lot of conceptual guides that instruct you on how to do particular things. So there's examples for each AI framework. There's a very large GitHub repo containing sample code for more or less every feature in the API. So there's a lot there to look at. The API reference I found as I was working through that, it wasn't so good. But because the API mirrored the CUDA API so closely, you could often kind of use that as a reference as well and expect behavior was generally pretty similar. In terms of features, you've got all your usual stuff that you would find in CUDA. So again, the sort of feature parity has been improving a lot. By the time we're on version 6.4, you got most of the familiar things. You've got all your memory synchronization. Pinned memory is in now, which wasn't for some time. Atomics and warp shuffles and things like that. We've got conditional syncs. So there's a lot of features in there. The streams, again, we can do concurrent execution. It's got its own graph API. So in general, feature parity is quite solid. There's a couple of things that are not in. So the independent thread scheduling is not something that exists on the AMD cards at the moment. I think you're just fixed with every thread in the warp kind of doing the same thing. And the AMD cards, I think this is maybe changing now. It's been a few months since we put the slides up, but they don't have the tensor cores in the same way for doing the matrix multiply add for AI. So you don't have access to matrix types and functions natively in the same way. But that's not to say that you can't use these cards still for those purposes. It just doesn't have the dedicated hardware. So yeah, there might well be more things that I don't know about. I'm not massively an expert. I just had a couple of months to have a play. So if anybody in the room, at the end has any thoughts as well, be happy to hear. So in terms of the tooling, again, you'll find I found the tooling quite complete. The compiler calls through to a Clang or MVCC backend, depending on whether you're compiling for AMD or CUDA. There are various profiling tools, as you would find with CUDA. We've got systems profiles, compute profiles for your kernels. There's debugging support, which again, you can force kind of synchronous kernel execution. If anybody's tried debugging GPU applications, it's not fun. So I think the tooling is very important for this kind of thing. And in terms of porting, we've got this HipFi tool, which we'll talk a bit more about in a few minutes. So libraries, obviously there's a lot of kind of industry standard libraries now with CUDA. Most of these have a mapping for HIP or ROC. So you'll notice here the distinction between HIP and ROCm becomes kind of important. Ones that have a HIP library but not a ROCm library probably mean you can access the CUDA version through the HIP API. If you compile for NVIDIA cards, you're good, but it maybe doesn't have an AMD equivalent. And there's some that have, again, a AMD equivalent, but do not support the HIP API. So depending on which libraries you're looking at using exactly, you might want to have a check on this reference and just check what you want to do is supported both ways. So in terms of AI, again, there's Docker images provided with ROCm setup and configuration appropriate for quite a lot of common AI toolkits. So it's quite easy to get started with. I didn't have a chance to play around with these, but they do exist. So I know performance portability is quite a big question. I found that yes, it's portable. Is it performant? This depends a lot. So depending on what you're doing, the hardware architecture is slightly different. And I know NVIDIA has kind of put a lot of work into providing optimized fundamentals for each of their cards. The AMD kind of equivalent isn't quite there yet, so performance isn't bad, but it's not specialized per device, which again, I think they are working on this, but right now, you might have to put a bit more work personally into optimizing for whichever device you're running on than you would with the equivalent NVIDIA card. But for simpler applications, you can get comparable performance out, and I think that's a good thing to strive for. So in terms of the kind of uptake and momentum of where it's going, I think it's on a strong trajectory. There's been a lot of growth in terms of the community and the support. The AMD cards are finding use in a lot of the top tier computers. So some of the exascale systems are using the Instinct line. The support for consumer cards is getting better, and they've kind of said that it's a goal for this to be, ROCm to be available on release with consumer cards as well. There's some serious work going into improving the AI performance. So with ROCm 7, just with a software upgrade from 6.4 to 7, you're getting kind of triple your performance in a lot of the AI frameworks, which maybe is still not quite as performant as the NVIDIA equivalent, but it's a lot better. We're also looking at developing this, the ROC repository, which is a build platform for just getting set up really quickly. So there's a lot of work in getting you up and running with HIP and ROCm very easily. So yeah, I kind of explored this through the lens of putting together this library of GPU primitives and then building a finite element code and a smooth particle hydrodynamics code. Again, nothing super complicated, but just as kind of a representative thing, so I could have a play and see what these were like. So this library will be available shortly. again, I had 2 months on the project. Our machine arrived broken. We sent it back. It arrived back after I'd finished the project. So I've not had quite as much time as I hoped to have to just test all of this and put it together. But this will be available shortly. I'll put it on the Slack when it is. And it's basically got a set of kind of fundamental operations with equivalent CUDA AMD code, some CMake infrastructure for compiling, building, benchmarking the two, so that you can easily just kind of try it out, compare what the code base looks like. And I think this would be useful for anybody who either just wants to have a look or would like to contribute as well. If you're happy to run the benchmark on some hardware that you've got, it'd be great to see you know, a bit more of that with different configurations. So again, this kind of what we've got in the code base is fairly simple, just kind of basic approaches to a lot of these algorithms. Some of them are put in optimized versions as well to a degree, so you can see kind of the process. We've got different levels of optimization, but for all the algorithms, there's like a base version where you can just see how it works in parallel, kind of in a naive implementation. We look between the CUDA and the HIP equivalents for this, for example, you can see the only real difference is you just find and replace CUDA with HIP, and this just works, which is nice. So if you're looking to do that, Hipify, we've got this kind of automated tool that AMD have put together. So this, you basically just run it on your code. There are two versions. There's a Perl version, which does just do a string replacement, and there's a version which uses Clang, which does pass your source tree, and that's a bit more rigorous. And that can also give you an estimate of how much of your code it's able to automatically convert, which is quite nice. So you can run this without affecting anything, get an idea of what the manual effort's going to look like. Again, depending on the feature you're using, you might hit 100%. I did for all of these primitive things, and it got most of the way there for sort of the representative applications. So yeah, our box was using the 7900 XTX, which is one of the latest cards. So I think it's got the best support probably. I didn't personally run into any issues with the software stack. We had a bit of trouble setting up, but it was fairly painless for me. So I found, yeah, with the kind of latest stuff, it's pretty good. So this is a bit of an example of what you might get out of Hipify. You can see just kind of listing off which functions it's converted. It'll give you some statistics about what you've converted overall, and so on. So I think looking forwards, like I say, ROCm 7 is coming along, and they're making the alignment closer and closer to the CUDA API. So Hipify should be even better at just taking your code and making it work. And there's some alternatives coming up. These are maybe of questionable legality in some cases. So there's Ludo, which is meant to be a drop-in replacement. You can just run the CUDA code on your AMD cards. But they did run into some legal issues. It seems to be back for now. It might go away again. We'll see. And there's also something called Scale, which is like a superset of CUDA and kind of does a similar thing. They've recently published a research paper. It's not completely covering the CUDA API, but it's pretty featureful. So right on time. Thank you very much.
So if parity with CUDA is desirable, what is the justification for having a different syntax at all? Why not start mirroring CUDA entirely?
So I think perhaps maybe somebody asked AMD the same question, and that's why they're moving further and further towards parity with the CUDA API. I think it's very sensible in terms of adoption for it to match. Obviously, there might be cases where the hardware differences mean you do need some kind of different functionality, like if you're accessing things in a different way, you have different resource available, it might necessitate some difference in the API. So I think the host side API certainly is very, very close. Some of the device API calls are a bit different. But yeah, I think there's probably not a massive justification. And yeah, they seem to be going that way with kind of a perfect mirror. So hopefully that answers your question.
So next then, are there any major architectural or performance benefits over AMD GPUs compared to NVIDIA ones?
Yeah, so in terms of architecture, the main thing that you would spot is the width of the warps, which for NVIDIA cards is basically always 32, and the AMD cards typically using 64 thread wide warp or wavefront. So this is one of the few things that if you're using Hipify or something, you might have to adjust yourself if you've got hard-coded like warp widths in. They do offer kind of a compile time constant for that, so it's kind of a find and replace. Performance-wise, it's obviously a bit hard to compare directly between two different vendors, but I think kind of a lot of it's always going to be how well you utilize the hardware, right? And I think the NVIDIA cards are obviously very well optimized already in terms of libraries from NVIDIA. I suspect the performance benefits will decrease as AMD improve their offering for kind of optimized fundamentals as well. Obviously, NVIDIA have slightly ahead in terms of features with their stuff like the thread scheduling and the tensor cores. So depending on your application, yeah, there might be a benefit one way or the other.
So one more question. Thank you, Anonymous, because I wanted to ask this question as well. So for portability, is HIP not a halfway house? You are now just locked into two vendors. Is general and open programming, or is a general and open programming library like SYCL not preferable in this case?
Yeah, I think that's a fair question and a fair concern. Yes, to a degree. I think it's kind of the simple answer. It's maybe still a kind of question of practicality. Like right now, those two are the most serious competitors, I think. Intel is obviously pushing things as well. And maybe down the line, yeah, you're looking at moving to something else. I think, so I don't have a lot of experience with SYCL. I understand it's potentially quite a different programming model. I'm not sure whether there are performance implications there in terms of how closely you're all like aligned with the hardware. So I'm maybe not the best person to answer that question, but it's a good question. Thank you.
Okay, so once more, I'd just like to thank Matthew there.